Hi everyone, welcome back to the channel. This is the 10th video in this dynamic programming series where we are solving 16 CSES dynamic programming problems, and we're also developing the right mindset to approach new DP problems. Now before you proceed with this video, let me also tell you that this video is a part of a series. In the very first video, we talked about developing the right mindset, understanding all of the concepts. Then we solved certain problems. Then we looked at few more concepts. And now this is the 10th video in the series, right? So if you're a complete beginner, I would recommend you to start the series from the very first video. So let's start by reading the problem statement. It is written that in an array which has n integers, all the values are between 1 and m, and the absolute difference between two adjacent values is at most 1. Okay. Now they've said that given a description of the array where some values may be unknown, your task is to count the number of arrays that match this description. Okay. So essentially, if you look at this example, they've told us that n is equal to 3, m is equal to 5. M is equal to 5 means that all the values in this array have to be between 1 and m. Wherever there is a 0, it means that this particular index does not contain any element right now. You have to fill it with an integer. So if you look at the number of different arrays that you could construct out of it, the answer is given as 3. So they've also given us the explanation here. Obviously these arrays 2, 1, 2, 2, 2, 2 and 2, 3, 2, they match the description. Why? Because if you fill a 1 here, look at this, 2, 1, the difference is 1. 1, 2, the difference is 1. Similarly here, if you look at these two 2's, the difference is at most 1, right? I mean at max 1 because the difference here is 0. Similarly here, 2, 2, 0. So 2, 3 here, the difference is 1 and 3, 2, the difference is 1, right? So given these constraints, n can go up till 10 to the power 5 and m can go from 1 to 100. Let's consider this example 230, 305. Okay. Look at this particular index, for example, 3. Can you change this index? No. You can only change the value of an index when it contains a 0. Let's look at this particular element. Can you think of what are the different values that can be put at this index? I think you can put a 2, you can also put a 3, and you can also put a 4. Now you look at this particular 0. What are the values that can be filled here so that the same condition follows? Clearly, if you put a, let's suppose 3 here. If you put a 3, then the difference between these two elements will be 0, but then the difference between these two elements will become 2. So that is not allowed. What about 5? Can you put a 5? No, the same thing happens. The difference between the last two elements is 0, but the difference between these two elements is 2. Correct? So what about 4? Can we put a 4? Yes, I can put a 4. So this clearly means that for this particular 0, I have 3 possibilities. And for this particular 0, I just have 1 possibility. Can you think of the number of different arrays, the number of different unique arrays that can be constructed with this given array? Clearly, it should be 3 multiplied by 1. Right? This also gives us a very big hint that, okay, the number of zeros that are there in the entire array, just consider all their possibilities and multiply all the number of ways. Correct? But there's a problem when you do something like this. Let's suppose if we look at the worst case here, right? The worst case could be this. All the elements are zeros. So what this would mean is that for every single element, you would have how many choices? You would have 1 to m choices. Correct? So for this you have m choices, for this you have m choices, and so on. For every single element you have m choices. And if there are n elements, how many total possibilities are these? These are clearly m to the power n possibilities. Will this work in our current time limit and the constraints? No, because m is going up till 100 and n is going up till 10 to the power 5. So clearly m to the power n will not work. But also think about this. Do we have some overlapping subproblems here? Like, do we have repetitions in terms of calculating our answers? And I would say yes. See, let's suppose, you fill the first element with a 1, you fill the second element with a 2, and then let's suppose you fill the third element with a 1. And now, let's suppose you just have one more element to be filled. Okay, here, it contains a 0, let's suppose. This is one problem. Similarly, look at this problem, 1, 1, 1, right? And then you have a 0 here. Okay, this is the entire array. N is equal to 4, and let's suppose m is equal to 3. Now look at the 0. This is the last element of the array. Okay, what does this depend upon? What can you fill here? Can I say it just depends on the previous element? What is there at the previous index? Similarly, in this case, it only depends on the value that is there in the previous index. So these, even though they look like different problems, they are essentially same problems, right? If I just know that the previous index was a 1, what do I know about the 0 then? I know that if the previous index was a 1, I can fill this element with 1, 2, I cannot fill it with a 3, right? So I already know the answer for this type of a subproblem, that considering a prefix like this 1, 2, 1, and if I just want to fill this last element which is a 0, I am not really concerned about the entire prefix. I am just concerned about the last element, right? What is the value present at the last index, right? So similarly, this problem, let's look at this problem, or let's suppose look at this problem, 2, 1, 1. All of these are same problems, right? If we solve this one particular problem, can I say I would also know the answer for this problem? I would also know the answer for this problem. What do I mean by saying this, that I can calculate the answer? It just simply means that, okay, if this is the prefix, how many different arrays can you construct considering there is a 0 at the last index? And I know the answer for this is 2, because I can fill the 0 with either a 1 or a 2. Now, when you look at this problem, can I say both these problems are just the same thing? You're essentially calculating it again, right? Because if you look at the last 0, it only depends on the value that was present at the previous index. In all these three problems, the value present at the previous index is the same, right? So what we know for a fact is that there are a lot of overlapping subproblems. We are going to do a lot of repetitions, right? So this should give us a very big hint that this problem can be solved with dynamic programming, okay? How do you think about, first of all, this case, that a problem can be solved with dynamic programming? A very obvious thing is that you are having repetitions in terms of calculating a particular value. Whenever you have something like this, the very first thing that should strike your mind is dynamic programming, okay? Now there is one thing that we discussed in the previous video when we were discussing this problem bookshop. We discussed this thing that whenever you are given an array and you somehow know that there is a dynamic programming solution involved here, what do? You don't think about the complete array at once. You start thinking about either a prefix of the array or a suffix of the array, right? So what I want you to do here is that think about, there is a very big array given to you. Can you break the array into a particular prefix or a particular suffix and then only care about that prefix or a suffix? Okay, so now that we know we only want to consider a certain prefix, you could pick up any prefix and start thinking about it. Let's pick up this prefix in our case here, okay? 020300. We are concerned about this prefix, right? So let's think about what can you fill at this last index here, right? We are only concerned about a prefix, this one. Let's think about what can you fill at the last 0. If m is equal to 5, can I say you can fill all the values from 1 to 5 at this last point? Yes. These are the different cases that you could construct when you fill the last element, correct? Now think about this thing, that okay, you have filled the last element with a particular value. What about the prefix before that here? What about the prefix before that? Can I say all of these become different subproblems now? Yes, all of these become different subproblems. Think about it like this. If you would have filled a 1 here, if you would have filled a 1 at the last index, what would you want to fill at the 0? And I would say you can only fill a 1 or a 2. Yes, I am concerned about this 0 now. What can you fill at the second last position, considering at the last position you have filled a 1? If you have filled a 2 at the last index, what can you fill at the second last index? And I would say you can fill either a 1, a 2 or a 3. What do you want? You just want that the difference, right? That the difference between the last element and the second last element should be how much? It should be at max 1, okay? Right, now similarly, if let's suppose there is a 3 here, what can you fill at this 0? You could fill a 2, 3 or a 4. Similarly, if there is a 4, you could fill it with a 3, 4 or a 5. If there is a 5, you can only fill it with a 4 or a 5. Right, so how do you need to look at it? There is a given prefix that you're considering. You are only concerned about what do I fill at the last index. And you said that I will consider all the possibilities, right? When you consider all these possibilities, what happens? When you put a 1 at the last index, there is a constraint that comes on the second last index. It means that you can only put a 1 or a 2 at the second last index, right? Similarly, if you would have filled the last index with a 2, it tells us that there is a constraint on the second last index. You can only put a 1, 2 or a 3. If you look at the entire array, you would have to think about what do you fill at all the zeros. But if you just look at a prefix, you are concerned about filling certain thing at the very last index and then reducing the prefix into a smaller prefix. So if you're looking at a prefix of size I and you said that the last index contains a k, what is the constraint that comes on the second last index? Or what is the constraint that comes on the prefix of length I minus 1, like from here to here? What is that constraint that comes on this prefix? The only constraint is that the second last index, this one, now should be either a k minus 1, a k or a k plus 1. Can I say this reduces down into 3 problems where we are saying that, okay, now consider the prefix of length I minus 1 such that the last element is k minus 1, such that the last element is k, and such that the last element is k plus 1. Yes, these are 3 smaller subproblems. In all these cases, I am concerned about a prefix of length I minus 1. Okay, and the last element being k minus 1, k or a k plus 1. Right? So this is how, this whole entire problem, you thought about just a prefix, and then this prefix kept getting reduced down to smaller prefixes. Right? This is what is happening here. Eventually what will happen is that, all these smaller subproblems will eventually depend on further smaller subproblems. Yes, and at the end you will hit a point where there is just one element left in the array, and you're trying to say that, okay, there is just one element left in the array. In this prefix, how many arrays can be constructed such that the last element or this element itself is equal to k? Right? This is the problem that you would be solving next. So now can I think about a DP state? Right? So now can I define my DP state like this, that DP of I comma k is equal to number of prefixes of length equal to I that can be formed such that the last element of the prefix is equal to k. If I define my DP state like this, I would know that this given problem breaks down into smaller 3 problems, right? Now again guys, it is very important to understand that in this problem, it was not at all obvious that this is going to be the state, right? But this is the mindset that we want to develop. We want to think about how can we break the problem into smaller subproblems and solve those smaller subproblems. If you start thinking along these lines, you will never have to remember a DP solution, okay? This will come with experience, right? So if you were to, let's suppose, solve this problem for every single prefix of length 1, length 2, length 3, so on up till length n, can we say you would have solved the entire problem? Yes, because ultimately you are just trying to find out number of prefixes of length n, right? Which also means the number of arrays of length n such that the last element is a given k. You could iterate over all these k's and sum up all the number of a's, right? So now let's try to think what is going to be the transition. Let's suppose I told you that the last element is a k, okay? And I told you that on the second last element, you can fill a k minus 1, you can fill a k, or you can fill a k plus 1. And I told you that the number of arrays that look like this is equal to 10. The number of arrays that look like this is equal to 20. And the number of arrays that look like this is equal to 5. Can I say the number of arrays that look like this, which have a k at the end, is nothing but the addition of all of these, right? So can I write my transition now? Yes. I can simply say dp of I comma k is equal to dp of I minus 1 comma k minus 1 plus dp of I minus 1 comma k plus dp of I minus 1 comma k plus 1, right? All these 3 different ways that are there, you will just add them up, right? So this is the transition equation. We clearly saw the state. We also know the transition equation. What is going to be the base case? Can I say that, okay, when the array is of length just 1, like this is the entire array that you were constructing. Let's suppose the subproblem size is just this much. We are only concerned about the subarray of size 1 or the prefix of size 1. Can I define my DP state for this just one element? And I can simply say that, okay, if this element was a 0, then I can fill anything here. But if this element was not a 0, can I fill anything here? No. So what this would mean is that, okay, dp of 1 comma k is equal to 1. There is just one way, if either the element is 0 or the element is equal to k itself. Okay, so if you look at this, see, when you have an array like this and the last element is a 0, can I put a 1 here? Yes, I can put a 2 here, I can put a 3 and so on. I can put all these values up till m. I can put all these values. But if the same value was not 0 but equal to, let's suppose, k, can I fill in any other value than k? No. So what I can say is that dp of 1 comma k is equal to 1 if a of 0, considering, let's suppose, 0 based indexing, if a of 0 is equal to k or a of 0 is equal to 0. If it is equal to 0, then yes, there is one way to fill it. You can fill it with that k itself. If a of 0 is already equal to k, then yes, there is one way as well. But it is equal to 0 otherwise. Okay. If, let's suppose, you are saying that the first element itself is a 10 and you are saying dp of 1 comma 20, that will not work because you cannot put 20 at the place of 10. It is already filled there, right? So this is the base case. Okay. what is going to be the final subproblem? So whenever you want to find out what is the final subproblem, there are just two things that you need to look at. First is, how did you define your state? What did you write in your state? And secondly, what is being asked in the problem statement? Now our state here is pretty simple. Number of prefixes of length I such that the last element is equal to k. So can I say I am concerned about the entire array, the number of different arrays? So dp of n comma 1, the number of prefixes of length n such that the last element is a 1. dp of n comma 2, number of prefixes of length n such that the last element is a 2, so on up till dp of n comma m, number of prefixes of length n such that the last element is an m, right? So what I know that the final subproblem is nothing but dp of n comma 1 plus dp of n comma 2, so on up till dp of n comma m, right? And you can also write it as like this. Right? This is the final subproblem. Got it? Alright, so now let's look at the code for the same problem. Firstly, I'm taking this input n and m. N is the number of elements in the array. M is the range of these elements, 1 to m. Next, I'm defining a 2D dp vector here, n cross m. In fact, n plus 1 cross m plus 1. Alright. And here I'm saying that dp of I comma k is equal to number of ways to build a prefix of size I, the same state that you are using, such that the last element of the prefix is k. Got it? Next, we are saying that, okay, this is the base case. Obviously, when there is just one element left in the prefix, the number of ways to construct that prefix could be either 1 or 0, right? And I am saying that, okay, dp of 1 comma I is equal to 1. What does this mean? It means that there is a prefix of length 1 and the last element itself is I. This is going to be 1 if you know the first element in the array, which is going to be a of 0, is either I or it is equal to 0. If it is not I and if it is not 0, then it clearly means that there is some other element present here. So you cannot have this element as I. In that case, dp of 1 comma I will be 0. Next, what we are saying is that we want to find dp of I comma k. And I told you that dp of I comma k depends on three values. I minus 1 comma k minus 1, I minus 1 comma k, and I minus 1 comma k plus 1. So when you look at the first dimension of this dp of I comma k, you will have to iterate from lower values to higher values because I comma k depends on previous values, I minus 1s, right? So here what I'm doing is I'm iterating from 2 to n. For dp of 1s, I've already defined the base case. And here I'm just iterating over these k's, which can go from 1 to m. Next, I'm saying that, okay, I am trying to find dp of I comma k here. Okay. Now, one thing that you must note is that if you're saying I want to put k as the last element, and if the last element itself is some other value than k, can you put the last element as k? No. So this is the case where I'm checking that, okay, if that particular element that you're trying to fill, if it is not equal to 0, and if it is not equal to k, in that case, it means it is filled with some other value. Then you can say that dp of I comma k is equal to 0 because there are no ways to construct a prefix of size I such that the last element is k. Okay. Next, what I'm saying is that, okay, I just have to consider three cases. So I'm saying k minus 1, k and k plus 1. So I've written a for loop for this. And why did I do this? Because I wanted to make it a little more generic. And I said that, okay, if you look at this value that you want to fill at the second last element, it can go from k minus 1 up till k plus 1. Right. Next, what I'm doing is that I'm writing this function called valid, which just clearly checks that, okay, the value that you're even trying to fill at the second last index, it has to be greater than equal to 1 and less than equal to m. So here I'm saying that, okay, if it is not a valid number, just continue. Don't consider this case. Otherwise, just say that dp of I comma k is equal to dp of I comma k plus dp of I minus 1 comma previous. Previous is this value going from k minus 1 up till k plus 1. Got it? Finally, how do I construct my answer? I've already told you that the final answer is going to be what? It is going to be the summation of all these dp of n comma 1, n comma 2, so on up till n comma m. Because eventually we are concerned about the number of different prefixes of length n such that the last element is either 1, 2, so on up till m. Okay. So here I'm just calculating my final answer here and here I'm printing it. Okay. Okay. So what is the time complexity for this? The formula for time complexity is very simple. Number of states multiplied by average transition time. Number of states are how much? N into m. dp of I comma k. I can go from 0 to n and k can go from 1 to m. So n cross m states, n into m states. Transition is how much? Your single state is just dependent on 3 states. So it is order of 1. Correct? Time complexity is order of n into m. Space complexity is also order of n into m because the number of states are n into m. So that is it for this video, guys. I hope you were able to understand this pretty cool problem. In case you were able to understand every single thing that I told you, just write down understood in the comment section. And if you have any doubts, feel free to comment down as well. and I would love to help you.